So welcome to the second session of today. As you know, at ACT, we try to do category theory, but also be applied and keep ties as close as possible to the industry. So here's the first speaker from the industry. We're very pleased to have Ghani from Symbolica, who's going to talk about approximate game theory.
So thank you very much. It makes me nervous to be in front of academics, as an industry person. I'm always wowed by the kind of super brains you all have. We're just simple people in industry. Forgive me if what I'm doing doesn't rise to the kind of intellectual heights that you're usually used to. I hope one day to become one of you. So, yes. So how long do I have?
You have about 25 minutes.
25 minutes, right. So I'll stop at 11:30. Right. So, as I say, so I'm this person, and I now work at Symbolica in London. And I'm going to give a talk on approximate game theory. So game theory is something that people have been studying for a long time. It's about how we make decisions. Oh, this is not working. Am I pressing it wrong? And it's been studied within the ACT community for a little while because it's very applied, but on the other hand, it has lots of categorical structure and has lots of compositionality involved. So it's familiar to a number of people in this room. But what I'm trying to do is add approximation to it. So approximation, basically, rather than searching for the best decision, which could take you a long time and could be quite hard, could we search for something that's not too bad, approximately good enough. So what I'm going to do is I'm going to talk about a particularly simple model of game theory called selection functions, and then talk about approximation for that particular model of game theory. And in order to try and validate what I do here, the approach I'm taking is compositional. So what I want to do is then say, well, this compositional approach to approximation in game theory, does it work well with the other compositional structure that people have identified? That's the kind of, is the mathematics good? It's good on itself, hopefully, but does it work well with the other mathematics? So that'll be approximation and compositionality. And then a lot of people have worked on open games, and some people are in the room here. I've seen Jules already, and Fabio, and various people. So then I'll take the simple models of selection functions of game theory and apply to open games, and then there'll be some conclusions. And I might mention some machine learning there. Right, so firstly, so why approximation? So approximation's been coming up quite a lot recently, and lots of people have been thinking about this, real valued this and that's, where things are not necessarily equal, or predicates that actually hold, but they hold approximately, or things are approximately equal. And I think this arises from a number of reasons. Paolo, can I let you do the admits? So why does approximation occur? So it occurs all over the place, of course. So sensor data might be approximate. Systems might have inherent stochasticity. Systems might have imperfect knowledge. We don't really know the state of the whole world. We only know some of it. Or exact solutions might be too complex to compute. So I think it's a really exciting research topic. Lots of people in the applied category theory community have started latching onto this and working on it. It's my little tiny contribution, but there's huge amounts of fascinating work going on here. And I'd recommend those of you who are thinking about other things to think about, because you've kind of solved all the problems with your aforementioned huge brains. I think it's a really cool area, and it's just taking off. So I certainly recommend it. So I'm going to take this general vision and apply it to game theory. So game theory is about how do we take decisions. So those of you who like politics and social structures and things like that are very interested in that. And here's a particularly simple model of game theory. These are called selection functions. So a selection function has type x to v to p of x. So basically the idea is, this is a utility function. You're trying to think about what x should you do. What's the best x to do? Now each x has a value. And so and then the selection function says, if I have one of these things, so this is a utility function, it assigns to every move a value. And the selections function says, give me a utility function, I'll give you a set of the best moves. And the obvious example is argmax. You take a function and say which x's are the best, and that's a set. But actually, game theory is really much more than argmax. Because, for example, if you've got decentralized systems with lots of components, then there is no global God who can say this is the best thing for everyone, because you've got these autonomous agents and they will do what they think is best for them. and therefore the equilibrium predicate you get won't be argmax. In fact, this is what's kicked off game theory in general. Nash equilibrium is exactly that realization. It's a different equilibrium predicate. The other thing I want you to notice is that this model of game theory works on all utility functions. And that's a hallmark of this kind of categorical compositional game theory that we've been doing for the last 5 or 6 years. Most game theory says, here's a utility function. But I think what we believe and what we've discovered, and we've got the mathematics to prove it, is that that's too limited. It's like you need to strengthen your induction hypothesis. You need more structure to develop a compositional theory. And one of the extra pieces of structure you need is to work with all utility functions simultaneously, not just one. Okay, so I mentioned about multi-agent systems and Nash equilibria that arises compositionally out of these things. So actually, you don't need to go as far as open games to do compositional game theory. Selection functions give you a little bit of compositionality. They can explain Nash equilibria. But then later on, we'll do open games because although you get a little bit of compositionality, you can't model sequential composition of games. What open games did was say, what further structure do we need in order to do sequential composition of open games? So we'll do some open games at the end of it. And that was Jules and Victor and Philip and myself. Right. Okay. So some key ideas and definitions. So if you've got a utility function, what are the best things you could do? What are the best moves? So one option is to say that an equilibrium for such a utility function is a set of moves, x, and what should x satisfy? Well, if you get the utility for x, and you consider the utility for any other possibility, this is better. So that's argmax. And that's fine, and that's where things kick off and if start in the subject. So this is all just stuff from the literature. In the literature, there is a notion of approximate equilibrium. They're called epsilon equilibria. So epsilon's a real number. It's a small little number usually. And what does it say? It says that, well, a possible move is an epsilon equilibrium of f, not if f of x is bigger than every other possible move, but you might have to add a little bit on. Or if you like, you might not be bigger than everything else, but you're not much smaller. So that's what an epsilon equilibrium is. And so if you like, this paper is about saying, okay, well, that's a very concrete definition in a very specific setting. How can we generalize that to the work we've been doing on compositional game theory, to selection functions and to open game? And as I've said before, while these two are instances of argmax, in general, we don't want to just be working with these kinds of things because they're very argmaxy. In general, when we study multi-agent systems, we're going to be going to things like Nash equilibria. So we've got to leave all this kind of stuff behind, very concrete, fiddly bits of first-order logic. So the question is, if we have our selection functions as a model, which can express these complicated equilibrium predicates, then can we define approximation for selection functions? So this is the key definition, and on this key slide, this is the key line. So if you want to look at anything, look at this line. If you like parsing first order logic, parse this line. If you don't, then I guess you should listen to me. Right. So the idea is we've got a selection function and it has some equilibrium. These are the best moves. That's a utility. Now, what happens when we kind of relax and say, okay, well, that's fine, but what about the approximate equilibrium? So I'm going to build you a new selection function, which is basically the old one, but with a kind of relaxed approximate equilibrium. So I'm going to imagine we've got our epsilon, which is a little number, and we're going to use some metrics because we're talking about approximation distances. So we'll have a metric on the function space, and the obvious one is a suit metric, but I mean, there are obvious generalizations of this. This is just approximation of predicates over metric spaces, but I've specialized in game theory. So here's the definition. What is this new selection function? Well, notice it has the same type. So we're not changing the moves, and we're not changing the values. Everything's the same. But now I'm going to have to define it. I'm going to say, well, if S is my original selection function, here's a new selection function. What are its equilibria? Well, I'm going to have to give you the equilibria for every utility function. I made that point earlier. So there's my utility function, F. So you might say, well, you could say X is in the equilibrium of F. X is in the equilibrium of my selection function S for the utility function F. That's what the selection function S is. But now we're saying you don't have to be in the equilibrium function. Sorry, you don't have to be in the equilibria of S for your selection function F. You can tweak F. You can, if you imagine over here, so there's my utility function, there's my moves, here's my values. So the selection function is S, there's a move x0, and it is in the equilibrium. The value is higher than everything else. But look at this point. This is actually in the equilibria, but it's not in the equilibrium of S because it's lower. But if I were to somehow give it a little bit more, so change F into a G, which kind of goes like this, it would be. So that's what this definition says. It says that X should be in the equilibrium for S, not at F, but at some other G. And what is G? G is not too far apart from F. It's within epsilon. So basically, you have your utility function, you can tweak it, add a little bit more, take a little bit away. And if you're in the equilibrium for that utility function, then you're in the equilibrium for this game. So it took me a while to find this, but I found it eventually, and it's nice and simple, captures an intuition, which I hope I've explained and you've got. It's very general, I think. I mean, we'll see that as I said, it's just metric, it's just approximation of predicates over metric spaces, basically. And it extends the usual definition. So that's all nice stuff, but is it good mathematically? So to be good mathematically, I want to say, does it have good properties in and of itself? And also, does it act well with all the other compositional operators? I say with the other compositional operators, because this is, of course, compositionality. We're taking a game and building a new game. So it's another compositional operator. Right. Okay. So let's talk about the mathematical properties. So we've got selection functions. We can consider what maps are of selection functions. So I've drawn this diagram over here to help you. So if you've got a selection function over x and v, and another selection function over x prime and v prime, you might say, what are the maps between them? And inside all of this game theory and inside a lot of machine learning and stuff, there are lenses lurking. I'm sure many of you know about lenses. So what is a map between this selection function and that one? It's a map between the underlying lenses, which preserves the predicates. It preserves the predicates contravariantly. Again, that's a property of lenses. If you've seen container work, you'll know the maps between containers have a contravariance. And this is what it says. It just says that you've got a map between the lenses such that whenever you have an equilibrium for the codomain, you get an equilibrium for the domain. And I've represented the utility functions from the codomain game and the states of the original game. And you can wrap this up in nice lens form. The state of x is mapped from 1 to x, and a utility function from x to b, x prime to b prime is just a lens map into 1. So this is a sort of, if you know the mathematics, it simplifies the notation. It's really cool. So I can just write alpha x, but this is lens composition and this is lens composition. Simplifies stuff. Okay, so we've got a notion of map between selection functions. And so we can observe that this operation is functorial. Basic trivial stuff that you want. And it's not obvious you're going to get these things. When you might have switched these orders the way around and said, I'm going to do this covariantly. Well, then it wouldn't be functorial. So it's not trivial, even though it might be simple. What else can we ask for? Well, we've got this index epsilon somewhere. No, there it is. We can look at the structure of the epsilon. So those who studied graded stuff could ask themselves, what about this epsilon? What about the structure of epsilon? Well, you can do some obvious things. So, there's the kind of, if epsilon 0, you don't change things. There's a kind of weakening rule that, if you approximate by this much, you certainly got as much as if you approximate by that much. And then there's a sort of transitivity of grading where you kind of add up the approximations. And that just follows from the triangle law for metric spaces. Right, 10 more minutes. Okay, compositionality. Okay, so that's this operator, this compositional operator for approximation, this T epsilon. What about the other compositional operators? So I've been going on about compositionality, but now I've got some motivation, although all of you know this. No one writes large code from scratch. You glue together pre-existing things. In general, for our models of the world, we should glue together pre-existing things. And our savior is, of course, category theory because it's about structure. That's the way I would do these things. So compositional game theory, that means building big games from small ones. And so there's a monoidal product on the category of lenses. It just takes on actual lenses, on actual pairs of objects. It's just the Cartesian stuff. But remember, lenses have a forward and a backward way. So when you extend this to the maps, you're not going to get anything Cartesian in general, although there are important special cases with reverse derivatives and things where you do get products. But we're not going there here. So this is just a monoidal structure. And the beautiful thing is that if you take two selection functions and apply this tensor, you can build a new selection function. And what will be the equilibrium? So you'll have to give me a utility function f, and its domain will be a pair of moves, and its codomain will be a pair of values. So you can say, when is a pair of moves in the equilibrium for the selection function, this compound composed selection function? Well, this is just the mathematics that arises from here. It says, well, x is going to be okay for the first agent if, well, x is okay for the first agent. But what utility function? Well, f takes two input. We're fixing the second player's move. And this will give me a pair of values. And I'm the first agent, so I only care about the first agent. And similarly, x prime needs to be happy. So that if the first agent doesn't change their move, is x prime happy? Well, they'll be happy with respect to their own utility function, their own selection function for the similar utility function. And the beautiful thing that when I saw this, I thought, oh my God, this is so beautiful, is that Nash equilibrium no longer is a primitive thing that was very cleverly discovered in the 50s and validated by experimental intuition. It's actually a non-primitive thing. It's actually just the product of two odd numbers. So that's very beautiful. It reminds me, yeah.
Sorry, what's that less than sign doing there?
Where?
In the x, between the x and the x prime.
This.
Oh, it's an and. Ah.
Oh, this.
Good.
Yes, it's yes. Sorry, I've not found out the perfectly academic way to write and. So that's just approximation. I guess I could write and with a little epsilon underneath it and see what happens. Yes, I mean, this is about sprinkling epsilons everywhere, but then trying to find out, well, maybe not everywhere, what's a nice place to sprinkle epsilons? Right. Okay, so 5 more minutes, I guess. Right. So what we've done is we've taken a selection function, which is essentially a function space index collection of predicates, and we've built a ball around it. For every utility function f, we don't take S of f, which is a certain set. We sort of build a ball around it by looking at the other g's that are close to f. So there's no particular reason that when you do that, it's going to respect the compositional structure that we've got. So, for example, tensors here. When I take some weird little predicate, I sort of, build a little ball around it, and then I operate on it. Well, that's going to destroy that little weirdnesses of what I started with, maybe. But actually, I was kind of really surprised, and that's what made me think, oh, we're onto something here, because the mathematics works. So, for example, you could ask yourself, if I take two selection functions, two models of games, and I put them in parallel composition, I take their Nash product, and then I weaken them, and I do it approximately. So what's an approximate Nash equilibrium? I don't know, per se, but it transpires, you can prove this. So an approximate Nash equilibrium consists of, it must be an approximate equilibrium for the first player and an approximate equilibrium for the second player. So that gives us some concrete stuff. It means if we want to find these things, it tells us to look inside. We don't have to start from scratch. That would be non-compositional. It means we can compositionally kind of look for these things by looking for the equilibrium of the first game, the approximate equilibrium of the first game, and the approximate equilibrium of the second game.
So it's 33 minutes later, so you have.
Okay, 33. Bad, yeah. Anyway, hopefully not the worst. Anyway, right, where do we get to? Right, yes, so applications. So these kind of mathematical theorems, I mean, this shows there's some kind of lax monoidal structure going on here. But these have concrete uses. It says how we can look for the approximate equilibrium of a Nash product through the component systems. But then, well, oh my God, I can do more. So the reverse is true as well, providing these sets of moves have a decidable equality. And that just is because, you've got some utility function and you've got these particular moves and you want to kind of tweak the utility at that particular point. So you need to be able to write a equation saying, well, you know, if I've got a move and has this utility, give it a little bit more, for all the others, leave them the same. So that's where the decidable equality turns up. Because it's all about tweaking utility functions. And then you can prove the reverse. So this is a really strong theorem, and I was totally surprised to get it, which is nice. In some sense, the best theorems are the ones that ought to be false, because you know, this can't be true. Bloody hell, it is. You know, wow.
Oh, thanks, John.
Sorry?
No, somebody forgot to.
Somebody forgot me. Such is life.
It's a problem on this time. All right.
Right. Okay, so like I said, very strong and unexpected. And so it says the approximate equilibrium of a compound system is exactly of those components. So that's really good. Right, so I'm going to have 5 more minutes. So I'm not going to totally tell you about open games. Those of you who know it will know that it's got a complicated little gnarly definition, which, you know, once you get the hang of it, sort of makes sense. But when you first see it, it's pretty gnarly. And it's been improved upon by a variety of different people over the years. But the best way is to ignore this gnarly definition and say, and again, phrase it in terms of lenses. I mean, lenses are beautiful. And you basically say an open game from, again, a pair of sets to another pair of sets. So you've got a set of strategies. These are like the moves now. We're separating moves from strategies. And then for every strategy, we have a lens. So in other words, some way of playing things and some way of feeding back utility. And also an equilibrium predicate. And since I put the strategies, I've indexed the equilibrium predicate by, you'll notice, oh, that looks similar to what we had before. It's a bit like a selection function. I mean, it's not exactly a selection function because that doesn't say X. But basically, it's a relation, predicate between utilities and moves. So we can apply the same thing to what we had before. We can do the same thing we did before. And so we basically say, if you've got an open game, you can build another one where you weaken it or you approximate by epsilon by saying for a particular strategy, a move is in the equilibrium for the approximated game at a particular utility function. If there is another utility function that's not too far away from it, and then your move is in the equilibrium predicate for the original game at that strategy for this approximated utility function. So it generalizes smoothly. The work we did on selection functions, it paves the way for this more complex open games material. Right, I'm going to now skip the rest. Oh no, I'm going to say one thing briefly. So you can go through the same thing before. You can prove functoriality, you can show it's lattice monoidal, and you can show it's monoidal if the moves are decided, same as before. But the point about introducing open games is that you also have another sequential operator, another compositional operator, sequential composition, and many more as well. I mean, it's not just that one. You don't want to tweak your definition every time you have a new operator. And so we can form this sort of sequential composition of open games. And here you only get a one-way inclusion, which is all I wanted to say. If you have something which is in the equilibrium of an approximated sequential composition, then you know it was in the equilibrium of the composite of the two approximated games. So we don't have backwards and forwards, we only have one way. That's still good for the first application of saying, if I want to know what are the equilibrium of this approximated compound game, well, I have some kind of, I've limited my search space. That's all you can get. Right, conclusion. So we've got a simple and compositional definition for the approximation of games. It has two key mathematical properties. It interacts surprisingly well with the other operators. A priori, there's no particular reason it should, but it does. And it has good graded structure. Future work. I think there's two things that I'd be interested in. One is a kind of metric game theory. So what's the difference between two games? How far apart are they from each other? Could you put a metric space on the space of games? Well, one thing is to say, well, take my two games. How much do I need to approximate one by so that the other is contained in it, and vice versa? So those of you who know about the Hausdorff metric will recognize where this comes from. So that gives you a distance. And then you can say, so if you wanted a quantitative game theory, you might say, I don't just want to put these two games together compositionally. I might say, well, if this is so far from this one and this is so far from this one, when I put these two together, how far away are they from these two? So that would be the kind of quantitative behavioral distances thing that you would do with game theory. And this would be kind of part of that. I think the other exciting thing, particularly for me as a kind of lowly industrial person working in machine learning, is that so I think we know, when I say we know, I'm not sure what the semantics of we is or the semantics of no, probably approximate, of course. But we know, we epsilon, no epsilon, the game theory and machine learning are much the same thing. So this whole program that I've been talking about could form the basis of a kind of explainable ML, quantitative ML, where you sprinkle your epsilons, you can track the epsilons as they move around, as they're computed. And when you learn something, you say, I've learned this, you actually get to know how much you've learned. And then you could also start, and if that epsilon is very low, you could say, oh, well, let's assume that it actually is this, and then proceed. There's a lot of things you could do once you start quantifying the learning process. And I should say the reason that machine learning and game theory are much the same is it's all about backpropagation. Okay, so thank you very much for listening to me, and I'll stop.
Right, thank you very much for the talk. There are a few questions. Okay.
I think you gave a living block.
Oh, thank you.
A name for the first three blocks would be almost surely. It seems like everything almost surely. For symbolic, industry leader, what are the applications of this to symbolic mission in strain by which you're on?
Right. So on Thursday, our boss, Dominic Verity, is going to give a talk, and he will tell you in general what we're doing. This stuff is not on our critical path. I mean, we're really focusing on machine learning code synthesis. If we were to have a broader, if we had a research division which forgot about short-term near-scale industrial impact, I would say that, well, it's about kind of, there's a lot of stuff in explainable ML where you have to say, okay, you've learned this. Well, are you sure you've learned it? What do you mean you've learned it? Can you give me some kind of evidence? So I think that would be to get a quantitative version, which would lead to ML verification.
All right. I don't think we're going to have time for all three questions. So maybe let's start from the far right.
Far right. Fabio, you're on the far right. Or should I call you Georgia?
So there's
Oh, sorry.
there's an evidence sort of 5 categories reference on games, and but when you sum up the results by saying that the T epsilon would say lax monodal, lax functor, endofunctor of the bi-category of open games.
You see,
So do you think that that's a nice general setting to work at these like
I would say that this is why I feel intimidated by you all academics, to be honest. Such a broad vision, with you know so much. All I can say is I don't know, maybe. It looked quite complicated to write it all out. And so, I chose not to. I chose to tell you the simple story. But yes, there is definitely the two-dimensional setting. There's, if you like, the types of the games, which describes the moves and the values and all that. There's the games themselves, and then there's the maps between the games. And you definitely want maps between the games because you want to characterize the games by universal properties. So you do want a two-dimensional approach at a minimum. And so, yes, there is definitely work to be done, but that's for academics, not for little people like you.
Okay, time for just one more question. Let's say Fabrizio.
Mine is an industry person, smooth brain question. So if you can go back to the definition of T epsilon something.
Yeah. Oh, I've lost the pointer.
Can you also
I'll probably put it in
It's
my.
there, it's there, it's there, it's there.
Wrong way around.
So basically here my question is how, since you are searching for a G over a metric space of functions, I guess that's where you need the complexity under the rock, right? So how top down is this problem? That's my question.
So basically you're asking me, the question of like, I mean, the nice thing about open games and stuff like this is because you have both all utility functions are considered, as well as all moves. Usually just all moves in one. So you've got both. You could reverse engineer stuff. You could say, if I have this, instead of giving a utility function what are its equilibria, you could say, I want this to be an equilibria. What utility functions can I have? So this is very interesting. And this is a nice application of open games. It's about policy definition. How do I set my tax rates to get certain behavior? So I interpret your question as, if I want something to be in an equilibrium, maybe an approximate equilibrium, how do I find my G to prove the statement? As you say, I didn't really consider it. I mean, I've been thinking about, finite games, finite move spaces. That situation, you could start doing research, you could start doing some things, but it's not a problem of investigating. As you say, it could well be described as hidden.
Right. Unfortunately, there's more questions, but we don't have time. Please keep them in mind and ask them offline.
Can I say,
Now,
can I just say, unfortunately, I can only be here today. So if you really are interested in asking me a question rather than just a little bit, come find me. I don't mind.
all right. So keep them in mind for 1 hour and ask him at the lunch break. For now, let's thank our speaker again.
Thank you.